Hi, I'm Park Ranger Joel Kane, your National Park Service host and friendly ranger guide for Earth Science Week here at Grand Canyon National Park, which we're celebrating with a week-long geology festival called GeoFest 2020. All week, every single day, I'm going to be sitting down for some wonderful talks with amazing geoscientists and educators from all over the country. People who have dedicated years of their lives to studying and researching and exploring this amazing place. Now, every day this week has a theme, different aspects of Grand Canyon geology that we're going to be talking about each day. And since today is the first full day of these talks with guest speakers, we decided to kick things off today with some fundamentals. We're going to be delving deep into the bedrock of Grand Canyon geology here today, pun intended. The theme for today is rocks. Now you might be thinking that's kind of silly. Isn't geology all about rocks? Well, yes and no. Geologists actually study a lot of different things, but rocks are kind of important. They're sort of a geologist's bread and butter. So that's why we're going to spend all day today talking about the different rocks that are found here in Grand Canyon. Because Grand Canyon, of course, is home to a lot of different and amazing rocks. Lots of folks walk up to the rim, look out over the canyon, see all these different rocks out here, all the different shapes and colors and sizes, and they start asking themselves, well, what are all those rocks out there? Where did they come from? Those are some of the questions we're going to be answering here today. Now, the rocks in Grand Canyon can be divided up into three big sets, or groups. And each of our talks today is going to be focusing on one of those sets. Although one of them is so big that we actually had to break it into two talks, the Grand Canyon Supergroup. Now in geology, we typically like to start with the oldest rocks and work our way into progressively younger and younger rocks, moving forward through time. Kind of makes sense that way. But that also means usually that we have to start with the lowermost rocks and work our way up, because of a law in geology called the law of superposition. You've got rocks, and then more rocks get laid down on top of those, and so on and so forth. The rocks higher up get progressively younger. So the oldest rocks are down there at the bottom, which is a little bit of a problem here at Grand Canyon, because our oldest rocks are all the way down here at the bottom of the Grand Canyon. They're kind of tough to get to. They're a little dark and mysterious, tucked way down here in the canyon's inner gorge, down where the Colorado River is, right behind me here. So I hiked down the South Kaibab Trail to get up and close and personal with these rocks so I can show them to you before we talk about them in our first talk here today. Now, they're called the Vishnu Basement rocks because they're actually a complex group of different rock types. Now, at one time, it was all known as the Vishnu Schist. But then a bunch of geologists, including our first speaker here today, came down here and mapped all of these basement rocks and actually figured out that there are a bunch of different rocks all mixed together very complexly. There's various metamorphic rocks, different types of schist and gneiss. There's different types of igneous rocks like granite and pegmatite. So like I said, they're kind of confusing and they are really hard to get to. I'll tell you, the first time I ever hiked down the South Kaibab Trail, I actually got a chance to get down here and touch these rocks in person. I was pretty excited. I was one happy park ranger. Now maybe some of you watching out there have had the opportunity to come down here and actually see these rocks in person. Those of you who haven't, maybe hopefully someday you will. But until then, please enjoy our first talk here today about these amazing rocks down at the bottom of Grand Canyon.
Well, hello everybody, and welcome to the first talk in our series of talks all week for Grand Canyon Geology Festival 2020 and Earth Science Week 2020. And our first talk here today appropriately starts with the rocks down at the very bottom of Grand Canyon, the Vishnu Basement rocks. As in geology, we like to start from the bottom and work our way up. So that's why behind me I've got a view from the Clear Creek Trail, looking down at the Colorado River, and a lot of these beautiful basement rocks across the river there with the South Kaibab Trail right there. And here to talk about those beautiful basement rocks at the bottom of Grand Canyon is Dr. Carl Karlstrom. He's a distinguished professor at the University of New Mexico. He grew up in Flagstaff, Arizona, and he started his Grand Canyon research as a professor at Northern Arizona University in Flagstaff from 1983 to 1991. And his focus there was on the basement rocks of Arizona. And with his PhD student, Brad Ilg, and MIT geochronologist Sam Bowring, and Sam's PhD student, David Hawkins, they determined new precise ages and new plate tectonic models for the tectonic evolution of the Vishnu basement rocks. And other new projects have come along on the younger rocks in the history of Grand Canyon, but the old projects never lose interest, and he has published refined ages and tectonic models with his recent PhD student, Mark Holland. And he's going to bring us up to date on that research in his talk here today. So Dr. Karlstrom, thank you so much for joining us.
Oh, thank you, Joel. It's fun to be here, and it's fun to think about a whole week of Grand Canyon geology. I thank you for organizing it and all the hard work in putting the program together.
Oh, you as well. You've done a lot of work putting this together as well. So.
All right, well, I'm going to share my screen here, which has a title slide for this talk. And so Grand Canyon's Vishnu basement rock. So we're talking, you got to turn a little switch in your brain for these rocks, maybe two switches. The first switch is time. We're going way back in time between 1.84 and 1.375 billion years ago. And then you got to turn that switch which says, okay, we're not looking at rocks which we can easily relate to things we're used to, like surface processes. Instead, we're talking about stuff that happened at depth. Rocks were melting, rocks were changing in the solid state, metamorphosing. So in a way, you can think of this as a journey to the middle part of the continental crust. Humans have been to the moon, but we've never been to the middle crust. So take this as an opportunity to go down the Grand Canyon, ask these rocks what they can tell us about what it's like down there in the middle crust and how they formed and how they got modified. This is I'm going to put on my EarthScope hat for this talk. EarthScope was a 2-decade experiment, kind of like the Hubble telescope for astronomers. The EarthScope experiment has allowed us to look deep beneath the North American continent and understand the timing and the structure of our continent, timing of assembly. So the basement rocks in Grand Canyon figure into this deep story and how North America came together. It's really the story, these rocks record the story of the assembly of the crust of the North American plate. So here we are looking west at Crystal Shear Zone, looking west into the Mojave province. And I just wanted to remind you, try and keep this at a variety of levels for everybody, of what is metamorphism, what is Plutanism. But there are these long series now of papers about the basement, which we can, they're peer-reviewed papers, we can go to literature and you can dig as deep into this as your time permits. But during this, this Earth Science Week, we're going to talk about the different chapters of Grand Canyon geology. I like to think of them as chapters. You can think of them as sets of rocks. Today's talk's about the Vishnu basement rocks, these one at the bottom. Chapter 2, the tilted supergroup layers. Chapter 3, the layered Paleozoic rocks. And then the carving of the landscape, which I wasn't interested at all when I was first working on the basement rocks. I am now, but you can think of these as different chapters that we need to each one understand as a separate sort of series of interesting puzzles. And we're the detectives, we're the geologists trying to figure out what happened during each of these chapters. If you want to see examples of these rocks, you don't want to go down the Grand Canyon, go to the Trail of Time, go to the Verkamps end of it, near the Grand Canyon Village. You can walk not far and you'll see a pedestal looks like this one at the bottom. Let me get my annotate button here, spotlight there. Okay, so the little red dot, this is an example of the oldest rock in Grand Canyon, the Ells Chasm Gneiss, 1.84 billion years old. That's here on the Trail of Time. Each of these little red dots would be 10 meters or 10 long steps. And then here are all the Vishnu basement rocks that are younger than the Elves Chasm, all bunched up between about 1650 and 1750 million years, MA for million years. So you can walk down just a few steps. You can get a variety of, let's see, all the variety of the interesting middle crustal rocks, which were collected in the bottom of the Grand Canyon, brought to you up for you to look at. Some of them are sliced nicely and polished. So it's a kind of a museum of the Vishnu basement rocks. So now let's go down in the bottom of the canyon, get a little bit of a field tour from up close and personal. It's kind of a fuzzy picture because it's an old one. This was my son Leaf a few decades ago in front of this frozen in magma factory, magma mixing factory. So this is what the guts of these magma chambers look like. These are kind of like immiscible bubbles, like oil and water with different compositions that don't quite mix, and so they're mingled. All these different flavors of melt in a magma chamber. And you can go and you can see folds in the Vishnu schist, the supracrustal rocks we call them, the metasedimentary rocks, that give us this idea that rocks flow. And that's why I went into structural geology. I was intrigued by the fact that rocks, solid as a rock, forget about that. At the right temperature and pressure, rocks will flow. So these are nice examples that get you thinking in this different mode. Middle crust, these rocks can flow. So they're moving at a certain rate depending on their viscosity. If you go down in the basement, you see that the layering is vertical, subvertical, but that's because these horizontal layers that were initially horizontal, as sediments always are, got tightly folded and squeezed, and this verticality of the Vishnu basement is due to this vertical folding of initially horizontal sediments. You can go down Pipe Creek and you can see the swirling. It looks like a cake batter that's been swirled around. And this is interfolded. The dark ones are called the Brahma schist, and the light ones are called the Rama schist. These are two different volcanic rocks that are folded together during this middle crustal deformation and metamorphism. If you go down to see the Zoroaster Pluton along the river, you can see pieces of that vertically was already foliated, this Vishnu schist, and got incorporated into this Zoroaster granite, and then all of it was truncated by a later pegmatite. So this is all happening in the middle crust. It's all hot. There's magmas at 1.74, and there's magmas at 1.68. And we can work out a bit of the history by dating these rocks and knowing which came first and which came second. Here's Mark Holland, recent PhD student, myself, George Garrels, who's going to talk later on in this week, and Mike Williams, who with his students did a lot of the metamorphism that I'm going to be reporting about. Okay, so where did these rocks form? I just showed you how, let's call them messed up. They're difficult, they're complicated rocks. They have a long history. They divulge their secrets only reluctantly. So we're the detectives, we're trying to figure out. So a lot of this stuff is our interpretations. And I have no problem saying that in the future these interpretations should and can change, but this is based on what we know as of 2020. So we think that the Vishnu schist formed in basins, these yellow basins that were between magmatic or volcanic arcs. And so the Rama and the Brahma schist are the volcanics, which exploded out of these volcanoes. And the Zoroaster granite and its cousins were the plutons, the deep magmas which fed those volcanics. And they were all related to subduction systems because these volcanic or magmatic arc chains build above subducting slabs. So it's a plate tectonic model for the formation of these rocks as volcanics and sedimentary and plutonic. And then when those get squeezed, this lower diagram, these island arcs come crashing together and form new continental crust. And we're looking at the record of that collision down here in this box, way down deep in the middle crust. And so it's a fragmentary record. It's one we pieced together, but it's spectacularly exposed in the canyon. Now, in terms of what temperatures and pressures we were at, sometimes we get out our microscopes here, our hand lenses, as geologists look carefully at the minerals. And here you see kind of a blown up slab with muscovite, the shiny stuff, and garnet, the round things. Then these brown starlights with beautiful starlight twins. The mineral stability of this assemblage can be determined by measuring the composition of the garnets, the starlights, the plagioclase that's in here. And we can get pressures and temperatures. So this is a PT diagram. Here's pressure going from 0 to a lot of pressure. And those correspond to depths from like the surface down to 30 kilometers. So we can determine the pressure analytically, and we can determine the temperature analytically with garnet and biotite. And we find that metamorphism of the Grand Canyon Vishnu basement rocks was between about 20 and 25 kilometers, so pretty darn deep and pretty darn hot, between about 500 and 700 degrees C. And you can see this yellow curve here is when rocks can start melting if there's water present. And so it's no surprise that some of these rocks in Grand Canyon are actually partially melting at these peak metamorphic conditions. Okay, so I jumped you into PT diagrams with no apologies. It's a little tough, but metamorphism can take place in any area there. Okay, so here are the arcs again, multiple subduction systems. We think a collision to form a mountain belt, the Vishnu Mountains, we affectionately call them. But it's in our mind's eye, right? Because those mountains have been eroded. So the now eroded Vishnu Mountains are exposed, the guts of them are exposed 20 kilometers, these were 20 kilometers deep below the highest peaks at the time of the metamorphism, which was about 1.7 billion. And here are these plutons down here, and the folding gives you kind of a glimpse of what the cross-section looks like. Now you can ask the question, where is this happening today? Where is continental crust forming for the first time, like North American crust was forming in the Vishnu basement of 1.7 billion. You can go to Australia. Australia is moving north. Well, you might not be able to travel there now because of COVID, but go there when you can. North America is moving north like this, and all these islands and fragments of plates in the Indonesian region are getting plastered one after another against the side of Australia. And that's our model for how the Western US formed. The stable craton would have been Wyoming in this case, so you'd have to flip this upside down. But all the rocks from Wyoming to Mexico smashed in one at a time to get added onto the continent. And so this is, we're looking, in a way, we're looking at a deep and old equivalent of something which we think is going on today. Okay, so just to summarize for a minute, the yellow here is the basins that became the Vishnu schist. They were sedimentary rocks, they get squeezed and metamorphosed, but they started at the Earth's surface. The plutonic rocks are these volcanic arc chains formed as a result of melting above a subducting slab. So that's our environment we envision for these now screwed up rocks. Let's look at their ages, and to find out more about their ages, we can use this little mineral down in the lower right, zircon. Zircon, we can get its uranium lead age, when did it crystallize, and we can look at its fingerprint, its compositional fingerprint of what its hafnium isotopes look like. It's a little bit advanced, but I think I can make it clear to you. First, we're going to just look at what are the grains that were washed in to the Vishnu basin, the Vishnu turbidite sediments. And we know that those sediments themselves are 1.75 billion because they're interlayered with the Rama and the Brahma schist. So we're looking at a rock that's 1.75, but let me show you it was kind of a surprise when Owen Schufeld, this is Owen, who worked on it maybe a decade ago. From this screwed up schist, he extracted these zircon grains, tiny crystals, and measured their age with uranium lead. And here's a graph of the number of grains, a histogram, and then the age. And the rocks are 1.75, and it's kind of comforting that no grains get younger than the age of the rock. You can't have a grain that was washed into a sedimentary rock that's older than that deposition. So that's good. But look at a lot of these 1.8 grains. and then not so many around 2.2 or so, and then a lot of 2.4, 2.5 grains. And lo and behold, the grains get as old as about 3.4 billion years old. So this was a big surprise to us. We were expecting all the grains to be about the age of 1.75, and instead we have this very distinctive bimodal two-peak ages of 1.8 and 2.4. And then we analyzed the compositions. This is the fingerprint business. And if the zircon was derived right from the Earth's mantle, first cycle, it'll plot on this depleted mantle curve. And if not, it was derived from still older crust. So this is rather amazing. This age rock, the 1.8s, which you see 1.8s, they project back to around 2.4. So those zircons were derived from the mantle about 2.4. These ones that are 2.4 were derived from the mantle that's more like 3 billion. So there's little zircon grain, and the assemblages in these both sedimentary and igneous rocks are telling us about a history of continental crust. So we are talking about first cycle continental crust development, but there was some old stuff nearby in these arcs. Now, if we went to the Pluton, so let's see, here's the Elves Chasm granite, this blue stuff, and here's the Vishnu schist over here. This is the Vishnu schist in pink. And we're going to collect, and here's the yellow, I meant the Zoroaster granite in pink. The Vishnu schist is the yellow, and all the way across from the eastern Grand Canyon all the way down to the lower Granite Gorge in the western Grand Canyon, this Vishnu schist has those same grains. So this must have been the same basin that got squeezed and shoved up on itself. And so we're just seeing the Vishnu schist in a bunch of places. But let's ask now, so we've learned something about the Vishnu schist. It's derived in part from really old grains that we don't quite know where they came from. But I'll show you where we think they did. Then we go to these Plutons and we say, okay, when you melted down in the lower crust and these melt source regions, what was down there? What does your fingerprint tell us about what your ancestry is? And I'll show you some results here, but this is the idea that instead of drilling a hole through the crust to see what's in the lower crust, we're just going to go ask the Pluton, okay, when you came up from the lower crust, what age stuff was down there? What's your fingerprint? So here's the upper Granite Gorge. You go into the basement about mile 78 at Hance Rapid. You go past Phantom Ranch here, go down, here's Elves Chasm itself, and the Elves Chasm Pluton, this oldest granite. And it turns out that these Plutons in the west, the purples here, had a different melt source region than these Plutons in the east. And we'd already proposed that this crystal shear zone was a very significant boundary, maybe a suture boundary between different arcs. So that was kind of interesting to see. So here, now if we go down to the lower diagram here, these green areas show that the crust that was melted is almost the same age as the Pluton itself. Whereas over here, there are these pieces, the brown is what's super interesting. That's the 2.5 really old bits of crust down there. And so anything west of this crystal shear zone, we call the Mojave Province. And there's evidence for these older source regions for the Plutons, whereas everywhere east of that, it looks like it's a first cycle development of continental material. So a big boundary there that separates the Yavapai province to the east from the Mojave province to the west. And here's what the zircons look like. And they sure see how prismatic they are. And they've got this nice igneous zoning and stuff. So that where that star is in the Boucher Pluton, which is about 1.73, we found an age, a core zircon of 2.5 billion. And it's hafnium model age from that spot on that zircon. These are about 0.2 of a millimeter. They're pretty small. But that zircon core itself was derived from crust that was nearly 3 billion years old. So that's one where we think that there's a sliver of really old Archean basement in the lower crust beneath the Grand Canyon, which we don't see anywhere at the surface. This is that hafnium diagram again. Elves Chasm, though, this one, the green, green is the east of the shear zone, and those were plotting right on the mantle evolution curve. So those Plutons were sucked out of the mantle. emplaced into the middle crust as magma chambers all at about the same time. Whereas the purple here, the Elves, that was sucked out of the mantle at 1.84, but it was also a juvenile first cycle granite. And the ones west of the crystal shear zone that had like that Boucher pluton, these ones have evidence for having a derivation from the mantle at an earlier time, way back to 3.3. So I just want to kind of, this is a fun little animation. We work on Grand Canyon rocks. They're so well exposed, and therefore we see more in them than many areas where geologists work. But there's global reverberations to what we learn because of the excellent exposures. So here's this Mojave province that I talked about. Here's the Elves Chasm Gneiss. We think they were separate blocks. And notice there's, at this time, 1.8, there's no Yavapai province. But here's Wyoming, called the Canadian Shield, the Archean core of our continent, against which new material was being added. So these two things came together probably by 1.76, that is the Elves Chasm and the Mojave. And here were these, in our model, these arcs, volcanic arcs offshore that then got welded against North America to form this new crust. And Grand Canyon just happens to go across the Crystal Shear Zone here, which is the boundary, the Gneiss Canyon Shear Zone here between the Mojave province and the Yavapai province. So it was a very significant place. And it's part of a bigger story where these provinces can be extended all the way across in the Rockies and into the eastern mid-continent. These red stars are places where Mark Holland studied the Mojave province in detail, from Death Valley and all across the Mojave. So when you go across the Crystal Shear Zone, you're into a zone where you're starting to see these older crustal bits, either sort of cryptic evidence for them in the hafnium isotopes and those occasional cores of zircons in Pluton. Okay, what was happening everywhere else? I keep showing North America. Well, here's that core of North America. Here's this Mojave province. And these rocks are so similar to rocks from the East Antarctica and Australia that we've proposed that this was, we call it the Oz-Wust connection, the Australian Western US connection, at about 1.7 or 1.8. We think that these old crystals, which we see in the Vishnu schist, may have come from Archean blocks very similar to these ones in Antarctica and Australia. And that same configuration still existed on Earth at the next supercontinent called Rodinia. This one is a fragment of the 1.7 or 1.8 billion year supercontinent. And then this is a little better understood Rodinia supercontinent at 1.0. Here, it's hard to see, you have to bend your head over. This is North America on its side at the equator, and Grand Canyon's over here. And over here's Australia, South China, Australia, the South American cratons around here, North China, Siberia, Baltica. This is the best that the community could do as of about 2008, this international project I was part of, to reconstruct the pre-Pangean supercontinent called Rodinia, billion years old. So we're still working on this, and as kind of just summarize the main points here. When you go in the basement, think hot, think deep, think differently. These rocks are trying to tell us their experience of in the middle crust as a continent was being assembled from collision of arcs, plate tectonic related to subduction zones. And then also, we're still working on it. This is a 2021 field forum, which we're going to run in September, with lots of interesting experts coming from all over the world to discuss how you develop first cycle continental crust. Is that plate tectonic model right, or how do we need to revise it? And can we get more precise ages of not only the rocks themselves, but how they cooled through time eventually to get to the surface below the Grand Canyon supergroup. So I think that's my last one. Should I end with Rodinia? No, let's end with Western North America and the provinces that were plastered on to the Archean Wyoming province to form all of the crust in Arizona and New Mexico. So thanks very much. I appreciate, I like talking about the basement. I can take off my Earthscope hat now.
All right. Well, awesome. Yeah. Thank you, Dr. Carlson, for that. Yeah, the basement rocks are just, they're enigmatic. They're way down there at the bottom of the canyon. They're hard to get to. It's hot down there. During the summer, it's hot down there.
Think of the middle crust when you're down there.
Oh yeah, exactly. Yeah, not quite as hot as that, but so as someone myself is primarily a sedimentary person. Yeah, they can be tricky and tough to really understand. Because and they have such a deep history.
Right.
And to think that they started out as sedimentary rocks, and of course, as sedimentary rocks, they have bits and pieces of even older rocks than that in them.
Yeah, that was a great contribution from Owen's detrital zircon work.
Mm-hmm.
Find out just how old that stuff is that got washed in.
Yeah, I appreciated that as something because I'm doing some detrital zircon work in my own thesis research. So
Okay.
I appreciated that quite a bit. Yeah, and it's always nice, to when you zap those crystals and you get surprises like that. Like, oh, what is this? Where did these come from?
Isn't that fun? I mean, in real time, you're seeing these ages roll off the mass spectrometer that sometimes can completely change our view of the rock units we're looking at.
Yeah. No. So no, that's awesome because like it's kind of hard to talk about them. To folks here on the rim of Grand Canyon because, like I said, they're way down there at the bottom, and even trying to point them out sometimes can be a little tough. It's like it's those black ones down there, the ones that aren't stacked in neat layers, and they look all messy, and they've got paint, shooting every which way through them. So.
Right. Those rocks that we brought up from the bottom to put along the Trail of Time, they really are good representations of the different units. And then this little walking guide that we put out called the Trail of Time Companion has a little story of each rock. And the story of each rock sometimes includes a little sketch. And if you look at that sketch and you go look, it's only a rock that's, they're pretty big, but they're not huge. But inside those rocks, if you look carefully there, you can see multiple events sometimes, multiple intrusions. You can see evidence for the folding. So it's a nice... it's easier to get there than down in the bottom. So I encourage people to kind of pull out the information from those specimens and then attack the ones in the bottom.
Yeah, absolutely. Yeah, there's one thing I wanted to ask you about in the one figure that you showed during the talk. Interspersed, throughout the region in a couple of different places, there are these things you had labeled as ultramafic slivers.
Ah, yes. So I know you know this, but an ultramafic rock is one that has very little quartz or none, and very little plagioclase feldspar of the kind that makes granites. So these are the rocks that make up the Earth's mantle, and they're made of olivine, pyroxene. Mostly we call them peridotites. So there's 3 or 4 slices of those in the Grand Canyon. The best exposed one is at mile 91. And that one, we just have a new paper coming out. It'll probably be in 2020, describing it as a cumulate rock, which means crystals, olivines, and the pyroxenes formed in a magma chamber, and then they settled to the bottom of the magma chamber and accumulated. So a cumulate rock with crystals that accumulated in layers, and we get the pressure and temperature of that cumulate layering. Turns out to be 30 kilometers deep that those rocks actually crystallize. So when I say they're slivers, what I mean is they were brought from 30 kilometers and thrust up into the middle crust where the rest of it's 20 kilometers. So they've been juxtaposed, brought up about 10 kilometers relative to the rest of the rocks around them. We initially thought they were pieces of the Earth's mantle, but now we think of them just as the deepest parts of these magmatic systems.
That's really cool and I think the one specifically you mentioned at mile 91 is the one that I've seen hiking along the Tonto Trail. And I was really excited. I'm pretty sure that's the one. And,
it might be.
I was really, because it's on the one I'm thinking of. It's on the north side of the river.
Oh yeah,
exposed,
okay, yep.
Exposed in the wall there.
Yeah.
Yeah, and I was looking for it. I was hiking the Tonto about 2 years ago, and when I spotted it, I was really, really excited. It's kind of like this dark greenish black, rock, and I was like, I know what that is, and that was really cool. So.
The research still going on, and that's what's so much fun. New students, new projects, new analytical tools, new questions, leading us to new knowledge about these rocks. But at the time of the Trail of Time, I love that ultramafic rock. I really wanted a piece on the trail, but what stopped us was we don't have the age of it. So we've tried bdelliite, uranium lead, zircon, uranium lead, various systems to try and date it. We haven't yet cracked it. We will, but we haven't cracked the age of it. Once we get the age done, I'll know where to put it on the Trail of Time. So.
All right. Well, I'll look forward to that.
Yes. Yeah.
Yeah. Thanks so much for giving us a really kind of close up and pun intended, in-depth look at these rocks. Because I remember the first time I ever hiked down to the bottom of the canyon, and the first time I actually got down to there and was able to touch them, I was really excited. I was really, really excited.
They are gnarly rocks. Powell called them the dreaded granite because when he entered into the Vishnu basement rocks on his trip, the rapids got harder because the rocks are harder to erode. And so to him, they were the dreaded granite. And they're dark and they're kind of foreboding, but beauty's in the eye of the beholder. So I find them beautiful.
Oh, they absolutely are. Yeah, they absolutely are. Especially in drainages where they've been really, really polished, like some of the pictures you showed. They're just beautiful.
Yeah. Amazing textures.
Hopefully you enjoyed that amazing talk by Dr. Carl Karlstrom about Grand Canyon's Vishnu basement rocks. Now, moving up the South Kaibab Trail a bit from where we were last time, I'm now standing in some layers of rock belonging to the next set of rocks that we're going to be talking about, the Grand Canyon Supergroup. Now, these are only a few layers of the Grand Canyon Supergroup. Specifically, they belong to a group within the supergroup called the Unkar Group. And that is going to be the subject of our next talk. As we'll learn, the Grand Canyon Supergroup originally was so thick, there's so much rock there, that we actually broke it up into two separate talks, discussing the lower part of the supergroup, the Unkar Group, which I'm standing in right now, and then the upper group of the Grand Canyon Supergroup, the Chuar Group. Now, back behind me here are some especially distinctive layers of the Unkar Group in the Grand Canyon Supergroup. These layers belong to a formation called the Hakatai Shale. Now, the Grand Canyon Supergroup is kind of enigmatic. It's a little bit confusing. A lot of park rangers don't even like to talk about it because it's only exposed, as we'll learn, in a few small areas within the canyon. Only in about 10% of Grand Canyon do you find layers belonging to the Grand Canyon Supergroup, for a lot of reasons which we're going to learn a lot more about. So a lot of folks, as they're standing up on the rim of the canyon, looking out at the view, they start asking, where are these supergroup rocks that these crazy geologists are talking about? And if you ever find yourself wondering that, look out at that view and look for these bright orange patches of Hakatai Shale, because that is a dead giveaway that you are looking at Grand Canyon Supergroup, specifically the Unkar Group. And like I said, that's the subject of our next talk.
Well, hello everybody, and welcome to the second talk for today, the first day of Grand Canyon Geology Festival, or GeoFest 2020. And our last talk, of course, from Dr. Karlstrom was on Grand Canyon's basement rocks. So the oldest, deepest rocks down there at the very bottom of Grand Canyon. And our second talk, as I said then, that we'd like to geology start from the bottom and work our way up. So the next talk, of course, is focusing on the next group of rocks above those basement rocks. And joining us here to talk about those rocks today is Dr. J. Michael Timmons. Dr. Timmons first visited Grand Canyon right after finishing high school, way back in 1989, as an apprentice guide on a river trip. And then for the next 15 years, he was a commercial river guide in Grand Canyon. During that time, he was captured by the geology of the canyon and eventually crossed paths with his advisors and colleagues at the University of New Mexico. While there at the University of New Mexico, he completed his master's and PhD degrees on the sedimentary and igneous rocks of the Grand Canyon supergroup, which is what we're talking about today, which is locally exposed down at the bottom of the canyon. He continues to explore the depths of Grand Canyon as a research geologist and deputy director at the New Mexico Bureau of Geology and Mineral Resources at New Mexico Tech. And he's the lead author on a stunning geologic map of Eastern Grand Canyon, numerous articles in technical and popular journals. And he and his colleagues at University of New Mexico and other institutions continue to probe the secrets of the ancient strata down in the depths of Grand Canyon. Dr. Timmons, thanks so much for being with us here today.
Thank you, Joel. Glad to be here.
And yeah, glad to have you. And so I mentioned it a couple minutes ago when we were talking before we started the program, but I chose my background here today, of course, because it is showing some of the rocks I think you'll probably be talking about. This view, if anybody is wondering, is from Moran Point on the south rim of Grand Canyon, which is a great place to go and see some of these rocks from up on the rim. So again, yeah, thanks for being here today.
Absolutely, yeah, nice choice of background. You got a lot of the stratigraphy there. All right, hopefully you can see my slide now. Okay, well, I'll just get right into it here. Thanks again for having me on this opportunity to talk about some Grand Canyon geology. I'm going to be talking about a particular section of rock from the Grand Canyon supergroup called the Unkar group of Grand Canyon. And this section of rocks, a billion-year-old glimpse into the Great Unconformity, and as I'll present here, a unique perspective on supercontinent assembly. So here's a classic photo for those river runners out there. You'll be familiar with this spot. This is near the scouting location above Hance Rapid, one of Grand Canyon's most awe-inspiring and frightening rapids. And this is always a good place to pause and ponder your next steps. And we're going to be looking at some of the geology that we see here in this screen. So Grand Canyon geologists like to break up the history, the geologic history of Grand Canyon into kind of chapters, much like you would think of a chapter in a book. And so Dr. Karlstrom talked about the Vishnu basement rock. We consider that chapter 1 of our story. I'm going to be talking a little bit about chapter 2, and then chapter 3, of course, is the flat-lying sedimentary strata of the Paleozoic. And then chapter 4, we consider the incision, the carving of Grand Canyon, and the complex history preserved in that record. So a little bit, some of this may be familiar with you, but I thought I'd give a little bit of background on some of the features we're going to be exploring here within the Grand Canyon supergroup. So for the new geologists out there, we as geologists look at breaks in the rock record just as much as we look at the rock record itself. We try and understand what these breaks in the rock records represent. And when we encounter a break in the rock record, they usually come in 3 different types. There's the non-conformity, which is in this first column. That's where, at least in the Grand Canyon example, we are taking a picture of geologic rocks as described by Dr. Karlstrom from the middle crust. And if you were to erode those rocks to the surface, some 1,250 million years ago in the case of the Unkar group, this is the relationship that you develop. And so that new erosional surface, and you start depositing sediments on that surface, the deposits are initially flat-lying and then may be disrupted through faulting or folding, and you can tilt that strata. Another erosional event might bevel those tilted strata, and new deposition may occur. And this presents a geologic relationship called an angular unconformity. Inherent in that contact is a history of early sedimentation on a nonconformity, deposition, and then tilting and beveling of those older strata before younger strata are deposited on that tilted strata. The disconformity represents a more subtle unconformity or gap in the rock record, and that's where there's some sort of cessation of deposition or an erosional surface where the sedimentary units are not tilted and new sedimentation occurs afterwards. So there's not a real clear break in the rock record. We usually identify these through erosional surfaces or a change in the fossil record. So in cartoon form, this kind of represents all these features that we're interested in as it relates to the Unkar group, which is shown in orange here, the tilted strata of the Unkar group. So at its base, we see the nonconformity with the Proterozoic or the ancient basement rocks of Grand Canyon, and they're overlain by sedimentary rocks that have been tilted. And then they are beveled and eroded before deposition of our chapter 3 rocks in the Paleozoic era. So this little cartoon kind of represents all the relationships that we see in unconformities. The great unconformity, which typically represents ancient metamorphic and igneous rocks beveled with the Cambrian age Tapete sandstone deposited right on it, but isolated in fault dropped or fault blocks are little isolated remnants of the supergroup, and that's what we're going to be looking at here. So let's get acquainted with the Grand Canyon supergroup. As I mentioned before, it is in non-conformity contact with the Granite Gorge rocks, the metamorphic and igneous rocks of the Granite Gorge. And there are two main groups of rocks within the Grand Canyon supergroup. The lower we call the Unkar group, and the upper we call the Chuar group. And the Chuar group is going to be described by Dr. Carol Daler in the presentation after mine. And so she'll give you all sorts of neat details about that part of the supergroup. We're going to concentrate on the Unkar group. And so the Unkar group is really made up of 5 main formations. The lowermost, Bass Formation, that transitions into the Hakatai Shale. There's a disconformity, so there's no angular relationship between the Hakatai and the Shinemu sandstone. It appears to be a flat surface, but there is a nice erosional surface to look at. The Shinemu sandstone grades right into the Docks Formation, and then the entire section's capped by basalts called the Cardenas basalt. So for the Grand Canyon supergroup, it's exposed, as I mentioned, in these isolated fault-bounded remnants along Grand Canyon. So shown in gray here are exposures of the Granite Gorge and the ancient rocks that Dr. Karlstrom described. Shown in red is the Unkar group, and you'll see these things in isolated outcrops all through the canyon. And then for the youngest part of the supergroup, the Chuar group is really only exposed here in eastern Grand Canyon. So part of this effort to understand these rocks is to map the geology, so map the distribution of all these formations, where are they located, and how do faults and folds relate to these deposits. And part of that is very very carefully describing the formation in what we call measured sections. And so for the measured section for the Unkar group, we see here at the bottom part, we see rocks like this. This is the Hatauda conglomerate, which is a very coarse deposit that's intimately interlayered with carbonates of the Bast Formation. And the Bast Formation has abundant features, stromatolites, all sorts of interesting biologic and sedimentary features preserved in these dolomites. These grade right into the Hakatai Shale, which is mostly very fine grained, but it does tend to coarsen towards the top of the section. And then we've got this disconformity before you get into the Shinemu Sandstone. And here's a picture of it, Hakatai Shale. You can see how sharp that contact is, but locally it is fairly irregular. And there's a nice lag pebble deposit at the base. The Shinemu Sandstone, as you move up section, has very interesting sedimentary features, including these convoluted beds. These are dewatering features within the rock. So as this rock, while it was still heavily saturated with fluids, we believe that we interpret these features as seismites. So you have an earthquake, you shake the saturated sands, and the water tends to move through those sands and contorts the beds. As you move up section into the Docks Formation, here you get into fine to medium sands, spectacular preserved bedding features, sedimentary features, so we can kind of learn about each of these formations from that. So part of understanding the geology is also understanding the processes of formation, but also the timing of formation. And so we now know from dating the very top of the section, the Cardenas basalt, that the top of the Unkar group is a little over 1 billion years old in age. If we use sedimentary grains preserved in these rocks to date these particular rocks. So in the case of the Cardenas basalt, we dated a mica grain that was next to one of these basalts and record the age of that basalt. In the Bast Formation, we look at zircons within the Bast Formation, and we've identified some ancient paleo ash layers within the Bast Formation. And these ash layers yield a couple populations of zircons that we can date. And it's interesting, these two populations come in two age populations as well. So we see these gray grains here are more rounded. They seem a little bit more recycled, and they tend to be older grains located here. So they're 1.8 billion years to about 1.4 billion years in age. Two big populations that tend to coincide with the age populations we see from the basement rocks. But there's this younger population that come from these very bright and very sharply faceted grains that we interpret as pristine or new grains at that time, and they yield an age of 1250 MA. We think that's the depositional age for the Bast Formation. So we bracket now the Unkar group between 1250 MA and 1100 million years ago. So 1250 million years ago and 1100 million years ago. With that important disconformity between the Hakatai and the Shinemu, and the duration of that, we don't really have a good handle on it, but it might be significant. So looking back at this map here, I want to kind of highlight now some of the structures we observed. We've kind of talked about the sediments themselves and their ages. Now let's look at the structures that we see. And what we see here are a number of northwest striking normal faults. These are down, we'll show pictures of these. And then we also see northeast, whoops, let me back up one. Northeast trending monoclines. And each of these features, each of these structural features are can be identified in the field, and they're beveled. They have been beveled just like the tilted strata themselves by the Tapete sandstone. We know these are ancient structures. So let's take a look at these. Here's an example of one of these monoclines. You can see the faults traced right here, passing right through here, where the basement rocks have been thrust up and over sedimentary rocks of the Unkar group. This is a shortening feature, and this is the Phantom Ranch fault right here. So there's a earlier history on that Phantom Ranch fault that represents kind of southeast side up relative to the other side there. In other locations, those monoclines are very subtle. In fact, we see sedimentary units actually come up and drape over these monoclines. And that's giving us a hint to when these monoclines were forming. So certain conglomerates, very coarse-grained deposits, actually pinch out and thin into very fine sands as it goes over the upthrown limb of this monocline. So here the fault didn't breach through the sediments, it just warps it. And the sedimentary record seems to respond to that or record that. Here a dolomite very uncharacteristically terminates here as it moves towards this ramp. And as you look closely at this section, there's a whole series of disturbed beds at this horizon. Very meter scale sandstone blocks that are disarticulated and moving from the upthrown side of the slope down the slope. This is telling us that this monocline, the development of this monocline, is happening while sedimentation's occurring. Now I want to kind of jump over to these northwest striking normal faults. Here's a photo of one. This again is by Phantom Ranch. And here again, you can see how these faults are truncated. Here's the Cambrian age Tapete sandstone. So Tapete's right on basement, Tapete's right on Grand Canyon Unkar group. And here's a fault trace going right through here. As we start dissecting the timing of these particular normal faults in the Unkar group, we need to look for faults that are truncated within the section. And we do find that by Palisades. Here's the Palisades fault. Again, we're looking towards the southeast here. And here's the main fault trace. But there are parallel to that subordinate faults that offset the lower part of the basalts, of the Cardenas basalts, but upper units are undisturbed. And these are tens of meters of offset across these features. So these are all hinting at, hey, these northwest faults, these normal faults are moving towards the end of Unkar time, or tend to be dominated by the Unkar time. And then finally, as we look at the broader relationships between the Unkar group and the younger Chuar group, we see an angular unconformity even between groups of the Grand Canyon supergroup. So here, clearly, the Unkar group had been faulted and tilted prior to deposition of the Chuar group, starting with the Nanquit Formation. I mentioned we look at these sedimentary grains and trying to understand where are they coming from, what ages do they represent, and so forth. So when we think about a little difference in dating an ash, when you're trying to date a specific moment in time, we can look at detrital grains to kind of gather a history of, well, where are these grains coming from? What terrains are they sampling as they erode one area and get deposited in a new basin, in this case, in the Unkar Basin? We look at the sedimentary features within the Unkar group, and we see that through a variety of sedimentary bed forms, we see a dominant northern transport direction for most of the Unkar group, from the Hakkatai, Shinemu, and the Docks Formation. A very strong indication that the source terrain we're looking for is somewhere south, present-day coordinates from Grand Canyon region. When we look at the composition of, or the age population for the grains within the Unkar group, for both the zircons, which are shown in black, and micas, which are shown in that red line, we see for the Bass Formation, these first two peaks are very familiar. They represent basically local basement rocks from the Paleoproterozoic and Mesoproterozoic. But there's this new population here at 1250. That's a new population starting in Unkar group time that persists through the entire section. The micas, as you look through this, represents local micas, basically. We're seeing micas from the older Granite Gorge and equivalent age rocks in the basement. But as you move up section, the micas definitely change populations here, and they're sourcing some new terrain that is as young as a billion years in age, and or 1.1 billion years in age. And we combine, these indicate a southern terrain with this age population. We look to the rest of the regional geology. And what do we know about this time period? Going through West Texas at this time is something we call the Grenville orogeny. This is a large mountain building event starting at about 1250 MA. And at that time, it's a magmatic arc with a classic subduction zone, and there's a basin on the interior, and volcanic ashes are being spewed and deposited into the basin. And we're seeing some of that. And we can correlate that to similar age rocks throughout the southwestern US, from central Arizona all the way proximal to this mountain building range. As we keep the clock moving forward in time, by about 1 billion years ago, we have something major happening. A continent is now colliding with North America at this time. And this changes the dynamics of this mountain building event. It becomes much larger scale, and we're depositing a lot more material into the continental interior. And so that's what we're seeing by Doc's time in the Grand Canyon supergroup and in all these sections here, all the way into the mid-continent region of the United States. Lots of detritus being deposited from south and these high mountains all the way into the continental interior. So what this represents for the Unkar group is an inboard record of a very ancient mountain event that's related to the assembly of a supercontinent that we call Rodinia. And much like the more recent supercontinent of Pangaea, Rodinia represented 1 billion years ago an amalgamation of all the continental fragments at that time. And here in Grand Canyon, we see some of that distal record from the margin of that, of one of those plate boundary interactions between one continent and another continent 1 billion years ago. And I'm going to leave us with this particular picture of really a long shot of the Unkar group in angular unconformity with all the overlying strata. And this kind of gets at how do you preserve a section of rock that's close to 2 kilometers thick underneath a section of Paleozoic strata that's only about 1 kilometer thick. You tilt it and you can show the entire thickness of that section. And with that, I guess I can take some questions from you, Joel. Thank you.
Yeah, and thank you. Yeah, absolutely. Thank you very much for that. Of course, talking about unconformities, we're going to be delving a little bit more into that with tomorrow's talks, with Wayne Ranney giving a talk on the distribution of supergroup outcrops in the canyon, why we see them, where we do, and Dr. Karlstrom really delving deep into the great unconformity or great unconformities, as he likes to say. So we'll be delving a lot more into that here in the next day. But that was a great intro to those ideas and concepts. So thank you very much for that.
Sure thing.
Yeah. So. Yeah, I mean the supergroup rocks are kind of enigmatic a lot of folks, a lot of rangers here who aren't geologists don't really even like to talk about them. They kind of ignore their existence a lot of the time because they're so difficult to talk about. And a lot of places, you know, from the rim, you can't even see them. So a lot of visitors to the canyon don't even realize that, you know, that they're down there. Even like you said, you know, and I try to impress this upon people when I do talk about the supergroup, is that it's way thicker than the flat-lying strata that we see out there today. I mean, that looks like a lot of rock when you look at those flat-lying Paleozoic rocks, but the supergroup down below it is way thicker. But it's just, you know, it's tilted and chopped up. So
yeah. So and there's a couple concepts there. So one is the much thicker representation of the Grand Canyon supergroup. So 2 kilometers for the Umpqua group, 1.6 kilometers for the Chuar group that Carol will be talking about, but also the kind of fragmentary record that's preserved today is also kind of enigmatic, right? So it's not exposed everywhere in Grand Canyon. And what I hope the talk kind of clarified was it's these faults that preserve, these ancient faults that preserve the Umpqua strata and the Chuar strata for us to see today. And we do see some of remnants of the Umpqua basin throughout the western U.S., but they're often buried by younger strata. Here we have the benefit of a Colorado River that is incised all the way through the Paleozoic section and given us a glimpse of that. So in many respects, Grand Canyon, without Grand Canyon being here, we may not know all that much about that time in Earth history. So it's incredibly important research to kind of, and important for Grand Canyon to understand how important that outcrop is to our understanding of that time period.
absolutely, yeah, and that's something that always just kind of boggles my mind and blows me away is the record of Earth history that's contained within Grand Canyon rocks. The fact that we can piece together and visualize things, you know, like a continental collision happening with North America, you know, hundreds of miles away, and you know, the assembly of a supercontinent predating, of course, a lot of folks have heard of Pangaea, and that's another thing when I talk to people here at the Canyon about the supergroup, I start talking about Rodinia, and most folks have never heard of it, you know, and
That's right.
you know, the farther back in time we go, you know, there were supercontinents before Pangaea, and of course, the farther back we go, the less we generally know about them. But we know a lot of, a lot of what we know about this one, thankfully, is right here at Grand Canyon.
Well, so I always think of geology as a classic forensic science, right? So we rarely have all the pieces to build our geologic narrative, but it's the collective effort of work that we've done here in Grand Canyon, work in Death Valley, work in other parts of North America and the world that help us piece these geologic stories together. And tying them all together is time, right? So if we can accurately date these deposits, we actually have a possibility of creating, you know, time consistent stories globally. That's a very critical element. And when you're looking at rocks of this age, and we don't have much of a fossil record to work with, not the classic fossil record that we lean on in the Paleozoic. So it's always been a challenge to correlate and kind of create common narratives across vast regions because we had no way of correlating them until we had really high resolution, high precision geochronology to date these rocks.
Yeah, and of course we'll be talking a lot more about dating rocks, geochronology, you know, a lot more about time here later on in the week. As far as dating the rocks, you know, one thing I did kind of wanted to ask if you talk a little bit more about is the Cardenas basalt up there at the top of the Umpqua group. As far as dating the rocks, I mean, that's pretty fortuitous, right? That we have an igneous unit capping the Umpqua group.
Correct.
And I know there's places where it's forming, where it it forms sills and actually like follows contacts between some of the sedimentary layers underneath.
Yes.
And I think there's some dikes associated with it too, like some diabase dikes that are cutting through in different places.
Yeah, so you got to think of those dikes and sills. So sills, of course, being intrusions that parallel sedimentary bedding, and dikes that cross a cut sedimentary bedding. The dikes we observe in the Unkar group often follow the fault traces of those ancient faults. So the fault has created a weakness that already cuts through the section, and the Cardenas basalt and the internal plumbing of those volcanic rocks are utilizing those weaknesses. And so it's also an indication of when those faults are forming. If you're getting that age of a basalt intruding along the fault plane, that fault plane was there, had to exist. So those are all interesting kind of observations we make out in the field to help us put a relative time context to the geology we're seeing, and then the age that we get on the basalt kinds of gives us the precision as far as when we think these events are happening.
Yeah, awesome. Yeah. I finally got down, actually it was not quite a year ago. For the first time, I hiked down New Hance Trail, got down to Hance Rapid. And it was weird. It was the first time being down at river level and not being surrounded by basement rocks. Actually having supergroup rocks there at river level was just really kind of felt strange. And there's this amazing dike right there at Hance Rapid cutting through Hackattai Shale, which I sat and stared at for I don't know how long, took a bunch of pictures of it, and
yes.
Yeah.
That is one of those, that's a classic one, and it's from the title slide. If you were to just change your focus, it was right above me in that photo. So right from the scouting location for Hance Rapid, it is right there. And it is a large feature. When you're across the river and looking across at it, it's hard to grasp, just like so many things in Grand Canyon, hard to grasp the scale of that feature. But it's a quite a thick dike there. And what you pass through moving or coming down Red Canyon on the New Hance Trail, you went through one of these Unkar age monoclines, and you crossed a Cardenas dike that intrudes along a fault plane. So it's all right there in Red Canyon, all the relationships that I described in this talk. So maybe a plug for that particular trail for the geologic enthusiasts.
Definitely for the geologic enthusiasts. Yes, it's not an easy trail, that's for sure.
No, it's not.
But it's an amazing hike. And I stopped for a little bit and took a look at the Bass limestone down in there. And there's this one bed that's just chock full of these beautiful oncolites.
Yes.
It's really amazing, and there's some really awesome ripple marks there. And I know some of the structures you showed in supergroup rocks, like those seismites in the Shinumo sandstone. I haven't had a chance to see those. I've seen pictures.
So those oncolites are interesting. That represents that transition from the Bass into the Hackattai Shale. And from a depositional environment, it's kind of interesting. Carbonates don't like mudstones so much. They want kind of clean, clear waters. But what that's telling us, those oncolites are, if you notice, they're in coarser grain deposits of the Hackattai. And so you have a fairly energetic environment, and you're ripping up the stromatolite oncolites, and they're kind of getting entrained into the lower part of the Hackattai. And that's what you're seeing there. And those pebbles of Hackattai, there's so much carbonate material, so much stromatolite activity, it's trying to grow on everything and then getting busted up by wave action and other things. So it was probably a very dynamic depositional environment, and there must have been just stromatolitic mats trying to coat everything, but struggling with all the new sediment that's coming into the system.
Yeah. And that just never ceases to amaze me. The stories that we can get out of just something like that, going back over 1 billion years, really incredible. I love talking about the faults in Grand Canyon, because some of them, like, date back over 1 billion years, back to the assembly of North America, or the formation of Rodinia, and they've been there that whole time, and they've even been reactivated at various times and done different things over the course of their lives. Those stories are just, I love telling those kinds of stories. So, yeah. Well, all right.
Yeah, they're very interesting features, and that's kind of given us clues to how, where to find deposits of this age in the subsurface elsewhere. You look to the structural presentation at the surface to maybe get a sense of, well, there may be Unkar age or Chuar age deposits underneath this feature, because it's a continuation of the same fault strand well into Utah. So they do offer very neat clues as to where to potentially find those deposits. They may not exist there because they've been eroded, but also just kind of, as you were getting at, just the kind of the persistence of those features in the crust, and how they're always ready to be reactivated by some new tectonic stress that might be placed on them. And Grand Canyon's, again, just a classic example of old ancient faults and repeat movement on ancient faults. It's very, very cool.
Yeah. All right. Well, thank you very much for joining us today, Dr. Timmons. I'm sure everyone appreciated your talk a lot, and hopefully we'll have some good questions for us here afterwards.
Great.
Yeah.
Thank you so much.
Right. Thanks.
Well, I hope you enjoyed that fascinating look into the Unkar group within the Grand Canyon supergroup. I've transported us off the South Kaibab Trail for a moment and brought us over here to the far eastern end of Grand Canyon, to one of my favorite views of Grand Canyon, Lippin Point. And it's one of my favorite viewpoints because you have such an amazing view of the Colorado River from here at Lippin Point. And that actually has a lot to do with the Unkar group that we were just talking about. You see, down here, the Colorado River is not cutting through those hard, strong, tough basement rocks that Dr. Karlstrom was talking about earlier. When it's cutting through those basement rocks, it's confined way down there in that deep, dark, narrow inner gorge. But over here, the Colorado is actually cutting through much softer layers of Dox sandstone within the Unkar group. And it's able to spread out and meander back and forth a lot more over here. So that's why you can see it so well. But I didn't just bring you over here for that view of the Colorado River or this amazing exposure of Unkar group down here below me. I brought us over here because the topic of our next talk is the Chuar group, the upper group within the Grand Canyon supergroup. And the Chuar group, well, is not exposed along the South Kaibab Trail. It's actually only exposed in one area of Grand Canyon, way over here in the eastern part of Grand Canyon. Actually up in that area right there. And the Chuar group rocks are so remote that I've never actually had a chance to go out there and see them up close and personal. The only way most folks ever really get to see the Chuar group rocks is on river trips, and even that involves a bit of a hike up from the river to actually reach those rocks, which is why I'm so excited for the next talk all about the Chuar group within the Grand Canyon supergroup, because these are some really, really amazing and beautiful rocks, and I hope to see them one day, but until then I'll have to satisfy myself with our next talk, and hopefully you'll enjoy it as well.
Hello, everybody, and welcome to another one of our talks here for the first full day of talks with our guest speakers for GeoFest 2020, celebrating Earth Science Week here at Grand Canyon National Park. And of course, today, for the first day of talks, we are starting with the rocks of Grand Canyon. Kind of important to a geologist, rocks. And we're going through each of the three main sets of rocks: the basement rocks, the supergroup, and the Paleozoic rocks. The supergroup is so large, there's so much rock that we actually divided it into two separate talks. And you just heard a talk about the Unkar group, the lower group of the supergroup. And now here to discuss with us the upper group of the Grand Canyon supergroup is Dr. Carol Deller from Utah State University. She got her master's degree in geology at Northern Arizona University down in Flagstaff, where I'm working on my master's degree, and her PhD at the University of New Mexico, which of course is where our two of our other conveners for GeoFest, Dr. Carl Karlstrom and Dr. Laura Crossie are. She did her PhD dissertation in part on basin analysis and carbon isotope stratigraphy of the Neoproterozoic Chuar group in Grand Canyon, Arizona, and has spent the years since collaborating with a lot of other folks who are also presenting here for GeoFest, including Dr. Karlstrom and Dr. Crossie there at UNM, and has been working on the Neoproterozoic and now is also working on the Cambrian rocks of Grand Canyon, looking at things like the snowball Earth hypothesis. And she uses various types of stratigraphy and geochronology to analyze and study these rocks. Dr. Deller, thank you very much for being with us here today.
Thanks for having me.
Yeah. All right. So we already heard a bit about the UNCAR group, and you're here to tell us about the Chuar group.
Indeed, I am. Thank you so much, and thank you to anybody out there who's listening or who cares. So yeah, I'm going to be talking about the Chuar group, as Joel so nicely put it, as the upper group in the Grand Canyon supergroup. And what we've been doing over the last 20 years is looking at this supergroup carefully and doing a lot of geochronology and field geology and figuring out that the supergroup is more complicated than we realized. But in some ways, it's actually, we've simplified some problems as well. So the Chuar group is a particularly cool rock unit that most people don't see when they come to the Grand Canyon. And you can see it in the background in this picture here. It's these beautiful variegated shales and carbonates and sandstones. And it goes clear up here and clear back down at the bottom of the photo. And then there's more beyond that. And we found that the Chuar group is a gift that just keeps on giving. So even in recent years, we've made new discoveries about things such as the age of the Chuar group and things about paleoecological implications for some of the fossil organisms that we find in the Chuar. So without further ado, Joel did mention, I didn't put all of my collaborators on this slide. I didn't put any of them because there's too many, but you can assume that most of the people that are giving GeoFest talks have collaborated with me on the Chuar group and also on the Bass Formation, the Mesoproterozoic Carbonate Unit and UNCAR group. And we have had NSF funding to help us work on the supergroup, and we now have NSF funding to work on the Cambrian. So I just want to give a shout out to the National Science Foundation. All right, let's get going. So here is a photo from Desert View Tower showing the Grand Canyon supergroup, and here's the Colorado River here. You can see the Cardenas lavas of the UNCAR group right here at river level, and it's faulted on either side. This is called Tanner Graben. Here's some of the red beds of the lower underlying UNCAR group. And then there's this funny unit here of red siltstones and sandstones called the Nankoweap Formation, and notice that that's unconformity bound in this interpretation. And then above that is the Chuar group, which is majorly divided into the Galeros Formation and the Quaggan Formation, and that's about 1,600 meters of strata. The Nanko is about 100 meters thick. Okay, so this next photograph, you'll see that yellow line changed to red because one of the things that we found is that the Nankoweap Formation, which used to be thought to be about 950 million years old, we now know is more like 770 million years old and is actually related to the Chuar group and is a new formation within the Chuar group. So the Chuar group grew by 100 meters, has a third formation at the base, and so we just have this one nice clean unconformity between the UNCAR group and all of this, which is the Chuar group, and that unconformity has a 300 million year duration represented by that surface. So here we are in the Eastern Grand Canyon, and the Chuar Group is shown here in orange. It's the only Chuar Group exposed at the Earth's surface. It's about 150 square kilometers, and Desert View is over here somewhere, and we were just looking at this little bit of Tanner Graben and the overlying Chuar there. The green is Unkar, and then the gray is crystalline basement. We're now going to go to this little polygon of Chuar, and there's going to be an image taken from here looking back to the east at the Butte Fault. Okay, so here's the Chuar Group in all its glory. Down here, well, I'll subdivide it in just a second. Let me show you the general setting, which is this green reverse fault known as the Butte Fault. It's faulting the Unkar group next to the Chuar group. Here's an older structure here faulting the Unkar next to the Paleozoic. And then here's Paleozoic directly overlying the Chuar group over on this western side. Let's see. We can divide the Chuar group. It was divided in formations as I showed you earlier, but the member names are a lot more useful. And so we have divided out actually Ford and Breed in the 70s, early 70s, subdivided out these different members. There's the Tanner, the Jupiter, the Carbon Canyon member, Dupa and Carbon Butte members, the Walcott member, and the Owatabee member, with the Walcott being the uppermost member. Oh, actually, I should say that the Butte Fault here was active during Chuar time. That's the work of Timmins and Karlstrom, et cetera. And so it was down to the west extensional fault while the Chuar group was being deposited, and some of this folding that you see here was actually developed during deposition of the Chuar group. All right, so here's a picture that's a bit complex of that Tanner Graben area again, and I just want to point out this Nankoweap formation here, these red siltstones and sandstones, and so it's now part of the Chuar group, and it has an age that's much more similar to the Chuar group than the underlying Cardenas basalts, and this unconformity here then represents 300 million years of missing time, with the Cardenas being about 1.1 billion years old, and then the Nankoweap and the rest of the Chuar group being between 770 and 729 million years ago. And those are new geochronologic constraints that I will tell you about in a little bit. So the pink here shows that this is where we are in the stratigraphic column, including the Nankoweap formation as part of the Chuar group. So moving up section, this is the Tanner member, which is mostly variegated but organic rich shales and some weathered organic rich shales. And that grades up into the Jupiter member, which at its base has this amazing stromatolitic complex. And this is the stromatolitic complex in a different canyon at Lava Chuar. And this is chock full of all different scales of stromatolites. And as a matter of fact, I was going to show you a picture, but I'm not going to do that. So also up in the Jupiter, besides its variegated shales, it also has interbedded sandstones and carbonates, and many of them are mud cracked, showing consistent exposure through time, and also filled chucky full of symmetric ripples, which indicate wave action. Another thing about, here's the Jupiter member. I broke it out, overlain by the Carbon Canyon, which I'll talk about in a minute, and here it overlies the Tanner member. This is known as the Chuar Valley, and this is Lava Chuar Canyon. Another important thing about the Tanner, Jupiter, and Carbon Canyon member is that, and Dupa actually, which is these red shales here, that they have a lot of abundant and diverse acritarchs, which are single-celled eukaryotes that probably photosynthesize. They have organic walls, and many of them are distinctive by the little, oops, sorry about that. They're distinctive based on little wrinkles and protuberances off of their outer organic wall. In the middle Chuar, there are a lot more carbonate beds, which is the basic subdivision between the Carbon Canyon and the Jupiter member, but otherwise it's probably a gradational contact. This is a very cyclic unit. There, Maya Elric is in that little pink circle somewhere, so you can get a sense for scale. So maybe this is 1.5 meters or 2 meters here. And you can see that there's shale and then a ridge, shale, ridge, shale, ridge, and those ridges are either sandstone or typically microbialite carbonates. Here's an example of just cryptalgal laminated dolomicrite. And you can see here that it's interbedded with organic rich shale that is actually mud cracked. So there's an anoxia problem going on in this part of the section. Another cool thing we find in this middle part of the Chuar group, the Carbon Canyon member, are these things that we call ribbons. This is bedding plane exposures of these really unusual striated, what we think are impressions of some kind of seagrass or macroalgae. You can see it here overlapping an interclast. Here's the bedding surface here. And from the side, you can see that it's at the very top of intraclastic conglomerate, probably indicating very shallow tidal to supertidal conditions. Other microbialites that we see in this middle part of the Chuar are the Bicalia, which is a type of stromatolite shown here, and we use that as a marker bed. The Chuar group has a lot of really nice marker beds. And then here are just some examples of very thinly bedded siltstones that have microbial textures on them. This one, these two are definitely what we call elephant skin, sort of a texture. And these are found amongst mud-cracked dolomicrites for the most part. So again, an area that was on and off exposed to air and then covered with water again. This is a very cool kind of mega mud crack. If you uncrinkle this fold here, it was probably at least a meter deep. And this is a carbonate, and this is a nice white powdery dolomicrite filling this crack in. And you see mud cracks of this scale in the Persian Gulf today. And I think that's probably what kind of conditions were going on at this time during Chuar group deposition. And this is actually a sandstone that overlies this, a cross-bedded sandstone. Speaking of sandstones in the middle Chuar, here is a really nice cross-bedded coarser grained sandstone, and you'll notice these angled, these inclined beds going like this, but then you can see these bed forms, these climbing bed forms, one here and one here, that are moving in the opposite direction and climbing up the inclined face of the dune, the remnant dune. So this is indicative of tidal conditions. And there are a lot of other symmetric ripples in the entire middle part of the Chuar group, indicating a north-south trending shoreline. And that's how with a lot of wave activity. So moving up into the upper part of the Chuar, these upper two members are very organic rich. The Awadabi member down here is super Martian colors, but enough organic rich shales that we could put together carbon isotope curve for both the Awadabi and then also the Walcott members of the Chuar group. Walcott is mostly organic rich shale, high TOC. It's got oolites and pisolites in it. And then at the very top, the 60 Mile Formation, which we used to think was the last chapter of the Chuar group, is now Cambrian in age. And it's always been Cambrian in age, but we didn't know that. But there will be other talks about the age of the 60 Mile and that it's now part of the Tapeats, part of the Tonto group. The stromatolites you see at the base of the Awadabi are, we call it the brain bed. This looks very brain-like. Sometimes it can take on slightly different weathering characteristics. And in the literature, this is referred to as Boxonia bicalia. And then this is an example of the really organic, rich black shales that you see in the Awadabi and especially the Walcott. And here's a TOC curve for the entire Chuar group, and you can see how there's increasing TOC values in this upper part of the Chuar group. And that's associated with sulfidic conditions and is thought to indicate at least anoxic bottom waters. This is a fossil that we find, it's a microfossil that we find in the Walcott Formation, and It is interpreted to be a testate amoeba by Susanna Porter, Andy Knoll, etc. And here's a modern testate amoeba to compare to this 730 million year old testate amoeba. So these fossils can be important as index fossils and also for understanding the food web at that time. Here's a thin section of pisolite/oolite that we find interbedded with the black shales in the Chuar group. And so even what could potentially be the deepest water in the Chuar group is not very deep because it's interbedded with these oolitic shoals. Here's just a picture of the 60 mile for to just have in your mind, but these clasts actually contain like 505 MA detrital zircon, so therefore this is no older than 505 million. So the 60 mile is Cambrian and not Neoproterozoic. Okay, so this is a slide to show you the older geochronology, the older geochronologic constraints on the Chuar, and then in red are some of the newer geochronologic constraints on the Chuar group. And so the UNCAR we have dated at 1.1 billion, and then in 2017 a paper came out to report that the Nankoweap had detrital sand grains in it of zircon that yield a uranium lead age of 782 MA, and that was kind of a generalized age with a pretty large error. At the same time, we got a 764 plus or minus 8 MA age using argon-argon on marcasite nodules in the basal part of the Awadabi, and then a long-standing uranium lead age on a tapaceous layer in the upper part of the Chuar that yields an age of 742 plus or minus 6 MA. So in recent years, and especially probably the last decade or two, there are higher precision geochronologic analytical tools that can take an age like 742 plus or minus 6, which is a pretty large error, down to a much more precise age. And this is 729 plus or minus 0.9 MA, so that's 900,000 years as an error for a Precambrian age, which is pretty cool. And down here, the 782 zircons we were able to reanalyze and got an age of, the youngest grain is 770 million years, so that is what we call the maximum depositional age of the Chuar group. And then Alan Rooney and others got 2 rhenium osmium ages on organic material found in some of the in the carbonates and marcasite nodules, and they got very consistent ages for this younging upward of 757 and a lot of change, and 751 and a lot of change. So this is an example of what these, whoops, I did it again. Let's go back. Here is what one of these, what's called a Concordia plot, shows for geochronologic analyses, and it's basically just the ratio of this lead isotope to this uranium isotope, and compared to this lead isotope and uranium-235. So these great big ellipses are LAICPMS ages, so these are laser ablation analyses, and they are much lower precision. And then the red ellipse is right here in the middle, and you can't even really see it. So let's go a little bit closer. All of these greens, I think there's 11 total, come in at about 775 with one young concordant grain at 770. So we're using this youngest grain, the 770 grain, as the oldest possible age that the Chuar can be. So it could be younger than that. It could be 10 million years younger than that, but probably not much more than that. And so, yeah, so we got the 775 population and the 770 MA population, which is actually only 1 grain. And you can see that these are very low errors. One thing I should note about the Chuar group is that it's chock full of microfossils. I mentioned the acritarchs earlier, and that they're single-celled eukaryotes, and they have all these different protuberances and textures that allow us to divide them up into different species. And one of these species is actually considered an index fossil for the middle Neoproterozoic. And you can see them over here. This is the one that we think is an index fossil, the Cerebrosphaera buicki. These are also acritarchs that are found within this lower part of the Chuar group. And then you notice that up where these red dots come in, we lose the majority of our acritarchs and we gain these vase-shaped microfossils, which are early testate amoebae. So the significance of our ages with respect to the fossil record in the Chuar group is pretty profound, because what we can say is that this index fossil, Cerebrosphaera buicki, consistently does come in at about 770 MA, which is based on a correlation with Australia, but that volcanic age over there is actually being reanalyzed, and the paper actually might be out by now. So what we can say is that there was significant diverse acritarch productivity between 770 and about 750, and that we had a change in the food web and an advancement in the food web complexity when these predators basically came along between 750 and 730 MA. Another really important thing is the kind of the ecology that we can learn about with respect to timing. These acritarchs actually have little predatory holes in them. This is based on some of Susanna Porter's work. And the vase-shaped microfossils also have little bites taken out of them that fit the size of the aperture of a vase-shaped microfossil. So we think that the testate amoebae were actually eating each other. So we can say that there was predation going on throughout Chuar time, and things eating each other going on between 750 and 730 MA. So interestingly, if you study the Chuar group for long enough, you can go other places and see rocks that look an awful lot like the Chuar group and also contain vase-shaped microfossils. And some of these units are the Uinta Mountain group and the correlative Big Cottonwood Formation here in Utah, and also the middle part of the Pahrump group in California. And so I'm going to show you some brief slides and some geochronologic data from Utah and California, and then compare them to our data from Arizona. So the Uinta Mountain group in Utah, here are the vase-shaped microfossils that have been discovered there. There's actually two here, and they're showing asexual reproduction. Excuse me, this is a photomicrograph, and these are on the order of tens of microns in length each. So invisible to the naked eye and about the same size as zircons. So the red pine shale is an organic rich shale that's like a kilometer thick, and it caps the Uinta Mountain group. And so with the vase-shaped microfossils and the organic rich shales, it's very, very Walcott like. It probably correlates with the Walcott. Lower down in the Uinta Mountain group, we've got beautiful breccias and conglomerates at the base, and those are interbedded with sandstones and siltstones, probably found delta complex here at the base. And we took samples from the very basal and sort of middle Uinta Mountain group for geochronology. And one really cool fossil in the Uinta Mountain group that Susanna Porter calls a scaly acritarch. You see that same scaly acritarch in the Chuar group, and so that would be consistent with them being correlative. So the geochronologic data for the Uinta Mountain group, you can see the big wide ellipses of the lower precision geochronology, and then you can see these blue and red ellipses of the higher precision analyses, and you can see these three ellipses coming in at about 766, and these three ellipses coming in at about 775. So the UMG has, oops, sorry. Ah, one more, sorry. The UMG has 6 grains, 3 of which are 775 MA and 3 of which are 766 MA, which is consistent with Mark Fanning's age from a few years back. And so even though there's 2 young populations, 766 MA is the maximum depositional age of the Chuar group. But interestingly, it has a 775 zircon population that is just like the one we see in the Chuar group. All right, in the middle Pahrump group, so all of these strata you see here are Pahrump group, and the Crystal Spring Formation is Mesoproterozoic, probably equivalent to the Unkar group, and it's unconformably overlain by the Horse Thief Springs Formation and the Beck Springs Formation, which are gradational between one another, and both contain V-shaped microfossils like this one shown here, which is again on the scale of 10 microns in length. There's the unconformity between the Mesoproterozoic part of the Pahrump group and then this Neoproterozoic part of the Pahrump group. And in these sandy breccias and conglomerates at the very base are where we find some of the zircons that we dated. And here's a Concordia plot for the LAICPMS, or the lower precision ellipses that suggest that the Pahrump group is, the middle Pahrump group is somewhere around 800 MA, but with these new higher precision analyses, we've got 3 grains here that come in at about 775, which is the same age of some populations that we see in both the Chuar and the Intermountain group. So what that's allowed us to do is make what's called a Wheeler diagram for the region from southeast Idaho over to Death Valley. And with our new geochronology, we've put all of these units, the Chuar, the Uinta Mountain group, and the Pahrump group, and also the Big Cottonwood Formation, based on Spencer's work, is that looks like we have a basin forming event, at least in the southwest and central US, between about 770 and 730 MA. And then there's a large amount of missing time, and you see this in Death Valley with the underlying units that are thought to be about 1.1 and are cross-cut by a 1.08 MA diabase. And then the 1.1, the youngest part of the Unkar group is 1.1. So you have this gap of about 300 million years of missing time, and that's consistent between Grand Canyon and Death Valley. Okay, the other thing we can do, there's a lot of things we can do with the Chuar group, but we looked at the organic rich shales shown here in black, and we looked at the carbonates shown in red, and we measured the carbon 13, carbon 12 isotope ratios throughout the section, and it makes this wiggle curve that's pretty radical. You don't see this in younger rocks, but you see this quite a bit in Neoproterozoic rocks. So we have this large excursion here that we call the Awadabi positive excursion. Comparing it to the Uinta Mountain group and the Pahrump group, also this is organic carbon, and this is organic carbon here in the UMG, and together both of those kind of show the shapes of parts of the Chuar curve. And so we think that there might be some correlation with respect to carbon isotopes. So using all these data, we're able to put together paleogeographic maps, complements of Ron Blakey. And so we have 3 time slices for the chump units. So here's the Death Valley, or the Pahrump group. Here's the Chuar group in Grand Canyon, Uinta Mountain group in eastern North Utah. So Ron's made these cool paleogeographic maps. We're generally in equatorial regions, but the equator went across like this. Okay, so this is modern plate tectonic configuration. So we would need to rotate this clockwise, and this would actually be facing north in Neoproterozoic time. So it'd be a north-facing margin. All of the data collectively show that we had a transgressive episode in early Chuar time, making these sort of epicontinental seas. It was connected with the ocean, and that's based on sedimentary structures, but also the diverse ornamented aquatarchs that we find. And that the biota was very diverse at this time. So a pretty healthy biota. In the middle of Chuar time, remember those supertidal mud cracks, and there's some red beds, and that's indicating a drop in sea level, probably making the Chuar Basin more restricted, and the diversity of the biota decreases. And then by 730 MA, we have another transgression depositing those really nice organic rich shales and pisollites, et cetera. Again, being more connected to the ocean. The testate amoebae arrive on the scene, and that's probably a jump in food web complexity. One of the last slides, we take this regional correlation, this chump correlation, and we extend it to the Yukon of North America, and also to Svalbard, which is an island off of Norway. All of these are considered to be Laurentian part of the Rodinia supercontinent that broke apart. And these vase-shaped microfossils shown down here are from each of these different units. So here's Grand Canyon, Utah, Uinta Mountain Group, Death Valley, Yukon, and Svalbard. And so the presence of these vase-shaped microfossils in combination with the carbon isotope stratigraphy from these two units, combined with the biota, the presence of the acritarchs, and then some new geochronologic ages that have come out of these units. I think it's pretty safe to say that this is a farther reaching phenomenon than just somewhere in southwestern US, and that we probably had mega regional or ultra regional, almost global connections of the oceans between definitely from this slide 750 to 730 MA. And this last slide shows one of the plate tectonic reconstructions. This one is Lee et al. 2008. And here you can see that Laurentia is rotated on the, and sitting on the equator. Here are the chump basins here. There's our Yukon basin. Here's our Svalbard basin. And then I took an example of just a few other units that are similar looking to the 2R, maybe organic rich, and have vase-shaped microfossils in them. And the Vizingzo now has an age of 760 MA. That's a new Rooney age that has not been published yet. And then these are also vase-shaped microfossil bearing successions here that have need more geochronology. So the idea of the chump hypothesis is not only were these three basins connected between 770 and 730 MA, but some of these other basins were very far reaching in different parts of the globe were also forming. And so this is probably a globally reaching basin formation between 770 and 730, and indicates overall pretty high sea level, not unlike what we see in Cretaceous time. And also we have rifting going on, still continued the breakup of Rodinia at this time. So this is probably an overall relatively warm time prior to the advent of the snowball Earth episodes that come at 717 MA. Alrighty, well, thank you for listening. I will be available for questions, and that's about it. Thank you.
So, wow, yeah. Thanks for your talk, because that was a really amazing look at well, some rocks in the canyon that I actually haven't had the opportunity to see, because they are exposed only in pretty remote area that's hard to get to. I actually haven't had the chance to see them up close, but they look amazing.
They are amazing. You would love at first sight.
No, I can see why. I can definitely see why. And geez, the amount of information and kind of like the big picture stories that you got out of those rocks that are exposed in this one little area in Eastern Grand Canyon is pretty amazing. That you're able to link them to other formations in the south, fairly close by, and then even also on a global scale.
Yeah.
So,
it's a hypothesis. So I need other people to test it for me, but I'm feeling pretty good about it. And I think we did probably have high sea level and flooded continents and a bunch of epicontinental seas all at the same time in that middle Neoproterozoic.
Very cool, yeah. So Dr. Karlstrom and Dr. Crossley at University of Mexico, who helped convene, the GeoFest, they gave a little discussion on the Trail of Time exhibit here on the South Rim of Grand Canyon. One thing that Dr. Crosstrom has said to me a number of times is that it's like, yeah, we probably overrepresented the supergroup. Because they've actually got pieces of different members, like they're on the Trail of Time, and they're gorgeous rocks. And I think they did it because they're so hard to get to and actually see. But if anybody does want to see some of these really beautiful rocks, with things like, mud cracked ripple marks, which were just incredible to see, they can go to the Trail of Time and actually check those out.
Yeah. And it just has, the Chuar has a cast of characters, and what's so amazing about it is it has so many distinctive layers that you can go from canyon to canyon and just find that layer again of like a stromatolite or the big mud cracks, and you know exactly where you are in the section because these are single unique layers, and all the stromatolites look different, and so it's really like a stratigrapher's dream, except for the fact that it's only exposed in this tiny little area in Grand Canyon.
Right.
It's really inconvenient to get to, by boat, and then you have to hike it an hour, and then you get into the rocks, and then you can start working.
Right. Yeah, you gotta love marker beds. They are incredibly useful. And I love, I love how much you talked about the fossils that are found in those rocks, the kind of web of life that existed on Earth during that time. Of course, very different from what we have on Earth today. But we're going to be hearing a lot more about those fossils actually on National Fossil Day here later in the week. And Dr. Susanna Porter is going to be giving a talk on those vase-shaped microfossils that you were talking about. So people have that to look forward to. So.
Susanna and I were both graduate students working side by side up all of those steep hills, and I would record the rocks, and she would take the sample for the paleontology.
Yeah.
So we go way back.
Collaboration. That's the name of the game.
That's
yeah.
Right.
So.
There's no way you could work on any of these units by yourself. There's just no way.
Yeah. So. Well, and I mean, I also love however much information you shared about the geochronology on those rocks. And again, we're going to be talking a lot more about geochronology later in the week as well, too. So,
so if there's anything you didn't understand in that geochronology part of the talk, wait till Mark Schmitz talks, and he'll fill in the gaps. And then these will be recorded, and then you can go back and watch some of these earlier talks that just kind of report the ages and show the graph, but he'll get down to the nitty gritty.
Definitely, yeah. And I love, especially when it comes to geochronology and how you're talking about how the Nankoweap is actually a lot younger than we thought it was, and now it's part of the Chuar. The 60 Mile was actually a lot younger than we thought it was, and now that's part of the Tonto group. It just shows, how we're always learning new things. Science is ever changing and evolving, and as our methods and techniques improve, the information we get improves, and we go back and revisit old ideas and say, hey, we were wrong about this,
Right.
So
who would think that these layers in the Grand Canyon would change, right? The names of right? Aren't they just set in stone, if you don't mind the pun? But yeah, it's been so exciting because we're pulling units out of the Precambrian and finding more missing time in the Precambrian, and finding that to be at least a regional phenomenon between, the Chuar rocks and the Death Valley rocks are incredibly similar.
Yeah, very cool. Yeah, that's just, it's crazy that we're still, I think the canyon still has so much to teach us, as much as we know about it, and as much work has been done over the past, 150 odd years. There's still a lot of stories out there, I think, to discover.
Absolutely. I agree.
Well, thanks for being with us today and discussing these kind of enigmatic rocks that are tucked out there in the canyon that I hope to go see at some point. Some of them are famous, like the brain bed that you mentioned. These are famous rocks, and at least in the geology world. So, yeah.
Well, maybe I'll be with you and we can go look at them together.
That sounds like a plan. So, all right. Well, again, thanks very much for talking with us here today. And of course, up next there is the Paleozoic rocks. So, all right. Thanks, everybody.
Okay, thanks.
Well, that about covers it for the supergroup. Hopefully after those last few talks, those basement and supergroup rocks down there near the bottom of the canyon are a little less mysterious. We're back here again along the South Kaibab Trail, a little bit below a point called Cedar Ridge, over 1,000 feet below the rim of the canyon. And behind me, you can see the third set of rocks that we're going to be talking about here today, the layered Paleozoic rocks. They take up most of the view looking out over the canyon from the rim because they're over 3,000 feet thick, from the Tapete Sandstone sitting way down there on basement rocks to the Kaibab Formation way up there on the rim. And they're still mostly flat-lying. They're responsible for a lot of the canyon's amazing topography and a lot of those beautiful colors that you see out there. Now, every one of those layers of rock is a different type of rock that was formed in a different depositional environment. And each one has its own story to tell about what our planet was like when these rocks were forming and how it was changing over time. Over several hundred million years of time, as a matter of fact. And the stories these rocks tell us are really incredible. Things like rising and falling sea levels, the uplift of mountains, and then the erosion of those mountains by rivers and streams, winds blowing giant sand dunes across vast deserts, the continents slowly inching their way across the face of the Earth. Some of these rocks even tell us about changes that were happening on the other side of the planet, like the rocks I'm standing on right now, as a matter of fact, the Supai group. So our next talk is going to be focusing on each one of these layers of rock and the stories they tell us about our planet's history. All right, well, hello again, everybody. And welcome to another one of our talks here for Grand Canyon Geology Festival 2020, or GeoFest, as we're calling it, 2020. Of course, here, the beginning of the week, we are talking about the rocks of Grand Canyon, the three kind of general sets of rocks that are found down in Grand Canyon. And of course, first we heard about the basement rocks down there at the very bottom, and then the Grand Canyon supergroup, that kind of strange and confusing group of tilted layers that are down there. And now in this talk, we're going to be hearing about the flat-lying strata of Grand Canyon, which constitutes most of the rock that you see out there when you look out into the canyon from the rim. Those are known as the layered Paleozoic rocks. And here to talk to us about those rocks is Dr. Ron Blakey, a professor emeritus at Northern Arizona University. He retired in 2009 after 34 years of teaching and research in the Department of Geology. And while he was at Northern Arizona University, he studied and published on the stratigraphy and sedimentology of many late Paleozoic and Mesozoic rock units on the Colorado Plateau. And his specific interests are aeolian and fluvial depositional systems, which nurtured his interest in paleogeography. And for the last 15 years, he's been heavily involved in producing paleogeographic maps from regional to global in scope. We've seen a lot of those amazing maps in various talks here today, and for the rest of the week, you'll be seeing more of them in other folks' talks as well. And many of those maps are on his website, deeptimemaps.com. And lately, he has merged those two disciplines into books, which have been published by the Grand Canyon Association, or now the Grand Canyon Conservancy. Ancient Landscapes of the Colorado Plateau, and Plate Tectonics, Continental Drift and Mountain Building, and Ancient Landscapes of Western North America. Ancient Landscapes of Western North America and the Colorado Plateau, both those books co-authored with Wayne Raney, who we'll be hearing from later in the week. And I own both of those books personally as well. I highly recommend them. He got his geology degrees from 3 universities, Wisconsin, Utah, and Iowa. And 2 years at Fort Hays, Kansas State, and then 34 years at Northern Arizona University. Many of his publications have been co-authored with students as well. And after he retired from Northern Arizona University, he and his wife Dee built the company Colorado Plateau Geosystems. And those beautiful paleogeographic maps are sold worldwide to museums energy corporations, academic institutions, and Ron and Dee currently reside in Carlsbad, California, where he's learning much different from geology than up here on the Colorado Plateau. So, Dr. Blakey, thank you very much for joining us here today. I'm sure you're aware you're a little bit of a legend at Northern Arizona University. That's, of course, where I'm working on my master's degree. And a lot of folks use those amazing maps that you make. So thanks for being here today.
Oh, you're welcome, Joel. And as Joel has just told you, I'm about to speak about the ancient landscapes of the paleogeography of the Colorado Plateau region. And I'll be emphasizing the Paleozoic rocks that are exposed within the canyon. In 2008, I published a book called Ancient Landscapes of the Colorado Plateau with co-author Wayne Ranney. And the premise of the book was that we could take the information from the rock record that hundreds, literally hundreds and hundreds of geologists have amassed over the years, and take this information and portray it in map form pictorially so that it looked like, in a sense, what the Earth would look like from outer space, from a satellite looking down on the Earth. And so this is why we call it, or I call it, the ancient landscapes. The Grand Canyon region is part of the Colorado Plateau. It's at the extreme western margin of the Colorado Plateau in northwestern Arizona. The Grand Canyon has a complex geologic history that perhaps we can break down a little bit more simply into 4 steps. The ancient mountains that form the continental crust in the bottom of the Grand Canyon and underneath the entire Colorado Plateau. The layers of sedimentary rocks that were deposited on top of this basement and form much of the landscape of both the Grand Canyon and the entire Colorado Plateau. The uplift of the Colorado Plateau, which occurred more recently, and then finally the carving of the present landscape of the Colorado Plateau, which occurred mostly in the last 5 to 6 million years. And by the way, when you see on my slides, you see like 70 to 40 MA. MA is Latin for mega annum, which means millions of years ago. So we'll use that shortcut when we talk about the age of these rocks. The geologic timescale shown here is also showing the various events of the Grand Canyon that I just talked about: the building of the basement, the sedimentation, the uplift and folding, and the carving of the landscape. And each of those events is shown opposite where it occurs on the geologic timescale. The focus of this talk will be the Cambrian through Triassic rocks of the Grand Canyon region. The Grand Canyon is part of the Grand Staircase, a magnificent display of rocks from the bottom of the Grand Canyon up to the tops, to the rims of Bryce Canyon National Park. These rocks are over 18,000 feet in thickness and range from rocks over 1,800 million years old to rocks as recent as 50 or 60 million years in the Bryce Canyon region. A lot of people ask, well, why isn't Bryce Canyon at 18,000 feet if the rock stack is 18,000 feet thick? Well, the answer you can see at the bottom of the slide here, which has a very low degree of exaggeration. You can see that the rocks are tilted gently to the north. So therefore, the younger rocks that are exposed further north are at lower elevations than they would be if it was perfectly flat lying. So the Bryce Canyon region, the highest parts are 8,000 to 9,000 feet in elevation, not 15,000 to 18,000 feet in elevation. Focusing in on the Grand Canyon proper, you can see again the rock ages of the Grand Canyon there from Cambrian through Permian and Triassic. You can see the rock names of the rocks that are exposed in the Grand Canyon. And these are the rocks that I'll be talking about in the rest of this talk. A few words about how these maps are made. We have to assess and incorporate an incredible amount of pertinent geologic data and interpretation from this data, and especially information that is easily shown on maps. I start by constructing a base map at a certain scale, a certain type of map projection, choose the time slices that will be presented in a given series. And I usually start by plotting the basic tectonic elements, where the mountains are there subduction zones, where are the big faults and elements like this. I then show the location of shorelines and uplands so that we can see the sort of the first order geography of the region, the sea versus the land, and the lowlands versus the uplands. Then I plot the various information from the sedimentary rocks, what we call the facies, or the aspects of those sedimentary rocks. And we relate these to their depositional systems and their climate zones and so forth. And then I spend some time looking for modern analogs to the various rock record. So if I'm dealing with a rock unit that is windblown or aeolian in origin, I go looking at places like North Africa and Saudi Arabia to find modern analogs. I then take I find these modern analogs, and I go to a program called GeoMap App. And in that program, and it's spelled exactly like it sounds, if you type that into Google, it will come up, and if you want to, you could actually use this program. It's free to use. And so it gives a map of the world, and you can focus in, and you can go to certain parts of the world. In the upper part of the screen here is a portion of northeastern China. You can see the vast mountain belts and the deserts and so forth present. So what I do is I take these elements on this digital elevation map, and I clone them in the program called Photoshop, and then I clone them onto the maps at the appropriate places. And you'll see as I go on here how that works. And of course, lots of checking and rechecking to look for errors and so forth. Here's an example. On the left is a digital elevation map. There you can see GeoMap App. If you just type that in, you can access that program. So the modern digital elevation map, this happens to be from Spain, and you can see that I clone that mountain range at the one end of the arrow, and at the tip of the arrow, it's pointing to an area in northern Canada and Alaska in the Devonian period, where I think there was a similar mountain range. And so I clone that mountain range in as shown there, again, using the tools in Photoshop. And of course, all this happens because of untold amounts of geologic data. It's absolutely impossible to do any paleogeography without an incredible background of information. And one last thing before I get to the paleogeography. In order to preserve sedimentary rocks, we need a place on Earth to put them, to put the sediment that forms the sedimentary rocks. We call this accommodation space. Parts of the world are rising, the mountains, the uplands, and parts of the Earth are sinking, the various basins. And in these basins is where modern sediment is deposited, and over time they get buried and eventually form sedimentary rocks. Okay, with that background, let's look at the Paleozoic paleogeography of the Grand Canyon region. Again, here's the time scale. We're going to emphasize the Cambrian through the Triassic. And on the photo on the right, we're looking in the Grand Canyon. The rocks at river level are Cambrian in age, and the reddish rocks at the very top of the photo are Permian in age. So we're seeing most of the Grand Canyon stratigraphy in this shot here. Okay, well, let's start at the oldest rocks, the Cambrian rocks, which are 542 to 488 MA, or millions of years ago. And we can see some various shots of what these Cambrian rocks look like across the Grand Canyon. And the shot in the upper left corner there actually shows right at the level where the sunglasses are. That's the contact between the basement rocks below and the sediment that forms the Tapete sandstone on top. And you can actually see some pebbles in the base of the Tapetes that were reworked from these basement rocks. So we can see a series of pictures here of what the Cambrian rocks look like. They've been fairly intensely studied. They're better exposed in Grand Canyon than probably anywhere else in the world. And from this information, we can create a paleogeographic map. This map would show the yellow rocks near the shoreline would be the Tapete sandstone, and the lighter areas to the left of that and below that would be where the Bright Angel Shale is being deposited. And so we might envision a modern beach, something like the picture shows on the right, with sand being deposited in the beach in shallow waters, and further offshore, muds being deposited that would be analogous to the Bright Angel Shale. Through time, the sea expanded in the Cambrian. It transgressed or crossed the landscape and moved quite a bit east into Colorado and parts of New Mexico and Wyoming. And this transgression is shown very dramatically by comparing this previous slide with this next slide. And there's about 30 million years between these two slides in terms of how much geologic time is represented. Analogous to the paleogeography shown here, let's say in east central Arizona, we could look at a place like the present-day coast of South Carolina, which is shown in an air photo in the upper right of the photo there, of the slide there. So we can see rivers and tidal flats, and this is the kind of landscape that probably was prevailing through much of the Cambrian. The Ordovician and Silurian rocks are missing from Grand Canyon. There is no record left behind. However, there are well-exposed Ordovician and Silurian rocks to both the west and south of the Grand Canyon region. And so what we can do is extrapolate or come up with ideas as to what might have been at the Grand Canyon during these periods of time, knowing that the rocks have been either not deposited or removed. And that's what these two slides show. The Devonian rocks are exposed discontinuously in Grand Canyon. In eastern Grand Canyon, if we look at the slide at the upper left, you see the surface that slants down from the left of the slide to the green shrubs at the bottom of the slide there. You see that the Devonian rocks are cut down into the older Cambrian rocks, and they're actually in what we call a channel. However, further west in Grand Canyon, the slide at the upper right, at the arrow, we can see the continuous band of Devonian rocks. We can also see the Devonian rocks well exposed to the south of Grand Canyon in the Verde Valley area of central Arizona. The Devonian landscape, the seas that expanded over much of western North America. There were a series of islands, and especially if you look in central Arizona, you see a series of islands that can actually be mapped out looking at places where the Devonian is absent. The rocks of the Devonian, again, were deposited in shorelines, such as the picture in the upper right, but many of the rocks were deposited in shallow, clear seas. And the picture in the lower right is an air view of the Bahamas, where the shallow waters of the Bahama region are full of carbonate material that deposit limestones. The Mississippian rocks They're also mostly limestones, and they occur through actually all of the Grand Canyon, and they form the magnificent Redwall Cliff. So the upper two slides show the Redwall limestone. The lower left slide shows the Redwall limestone in Verde Valley, and the lower right slide shows the part of the Redwall limestone exposed in Marble Canyon near the head of Grand Canyon. So the seas expanded greatly across the region. There was still some land, especially in northern New Mexico and eastern Arizona. And the environments range from tidal pools like shown in the upper right to, again, large, shallow, carbonate-rich seas, shallow, warm water. Organisms flourished. They died. They left their fossil record to form the Redwall limestone. The Pennsylvanian rocks from about 318 to 299 million years ago are, again, well exposed through the Grand Canyon. The two slides on the left show the part of the Supai group in the Grand Canyon. The slide on the upper right shows Pennsylvanian rocks at the famous goosenecks of the San Juan River in southern Utah. And the slide at the bottom right shows the Pennsylvanian rocks of the Supai group exposed in Verde Valley. I'm going to show you two of the Pennsylvanian formations here with maps. The Manicachaw Formation, which is part of the Supai group, was deposited as a series of dunes shown with the yellow pattern there, and coastal plains and beaches in similar environments. Something like what we see in the slides on the right. The right, we can see coastal dunes, and this happens to be Morro Bay, California, with very large coastal dunes. And on the right, near Pismo Beach, California, we can see a sluggish stream carrying sand entering the ocean and depositing sand along the shoreline. Incidentally, the Manicachaw Formation is the oldest formation in the western U.S. that has substantial aeolian or wind-deposited rocks in it. The Waskogami Formation is similar to the Manicachaw, also contains sand dune deposits, shoreline deposits, estuarine and tidal deposits, and so forth. The slide on the right shows a mixture of different environments. The light areas are dune areas. The more grayish areas are salt flats and river plains and so forth. You can see some standing water. So very complex environments. The Permian rocks at the rim of the Grand Canyon from 299 to about 250 million years ago formed the rocks all the way up to the rim. You can see on the upper left screen, you can see the Permian rocks of Grand Canyon. To the lower left, you can see the Permian rocks at Canyon de Chelly National Monument. In the upper right, you can see Permian rocks near Sedona, Arizona. And on the lower right, you can see Permian rocks at Monument Valley on the Arizona-Utah border. So I'm going to show you a series of maps that show us what the Permian was like. And we're going to see these environments changing fairly drastically over time. The Permian was very, very complicated period of time with changing environments. The first slide shows the famous Esplanade Sandstone, which forms a major cliff, major red cliff near the rim, but not at the rim of Grand Canyon. And its counterpart up in Utah is the Cedar Mesa Sandstone. And this formed a fairly vast coastal and inland dune complex along the seas to the west. In the upper right, we can see a dune field. In the lower right, we can see an air view of dune fields in central Baja, Mexico, where we can see the dunes and the tidal inlets and very complicated little environments. We find these in both the Cedar Mesa and the Esplanade. The Hermit Formation is a vast red bed deposit. It's the darkest red deposit in the Grand Canyon. It almost always forms slopes. And it formed in a series of rivers, both braided streams and meandering streams. The stream in the upper right, the modern stream in the upper right, is a braided stream that has multiple channels with sandbars in between the channels. The stream deposit, or the stream in the lower right, is a meandering stream. And we find both kinds of these stream deposits within the Hermit Formation. The Coconino Sandstone, probably the largest expanse of Permian sand across the southern Colorado Plateau, extends all the way into New Mexico and almost into southern Arizona. Again, it formed in a series of dunes. We can see a photograph of the Coconino in Oak Creek Canyon, between Flagstaff and Sedona. And we can see, of course, the great Coconino Cliff in Grand Canyon in the lower right. So a huge mass of windblown sand that extended over 2/3 to 3/4 of Arizona. A little bit later in the Permian, the Toroweap Sea expanded across western Arizona, but it only got across the western part of the state. Further east, the dunes continued. So to the east is the upper part of the Coconino Sandstone. And up in Utah, that sandstone is called the White Rim Sandstone, a very prominent unit in Canyonlands National Park. So we can envision a Toroweap shoreline looking something like the slide in the upper right, which is the modern coastline of South Carolina. And we could imagine the inland dunes looking something like this dune field in Western Africa. The Kaibab Formation was a further expansion of the sea. The Kaibab moved across, covering almost all of Arizona, almost all of Utah, much of New Mexico. There it's called the San Andreas limestone. So again, we can envision, like the picture at the upper right, a vast shallow sea with carbonate material, shoals of carbonate material, shoals full of fossil debris and so forth. And in fact, there in the lower right, we can see one of the brachiopods exposed right on the rim of the Grand Canyon in the Kaibab. That's a dime for scale. So the Kaibab forms the rim of the Grand Canyon, but exposed within Grand Canyon National Park and on the slopes adjacent to the Grand Canyon are Triassic rocks. These rocks formed from about 250 to about 200 million years ago. And we can see the upper left, the Moenkopi Formation, the slide, and that's in southern Utah. The slide to the upper right is at the Paria area of southern Utah. The brown rocks in the foreground are Moenkopi, and the rainbow-colored rocks in the middle part of the slide there are the Chinle Formation. And then in Petrified Forest National Park, in the bottom, we can see the Chinle Formation. So these rocks were once covered the entire Grand Canyon region until the Colorado River cut down through and removed them. So the Moenkopi Formation was deposited as a series of probably ephemeral streams, that is, streams that aren't flowing all the time. They flow during wet periods, and they could be bone dry during more arid periods. But there was a shallow sea across much of Utah, and these rivers flowed into that shallow sea. And so the Moenkopi in places is non-marine. fluvial or riverine deposits, and in other places it's marine deposits. The slide in the upper right shows the kind of streams that much of the Moen Kopje may have been deposited in. The streams are desiccated at present when this photo was taken. They're ephemeral, they have no water in them at this point, but should the region receive a lot of rainfall, those streams would be full of water, carrying a lot of sediment. The shot on the right is modern day Rocky Point, Mexico, vast tidal flats, very similar to what we see in parts of the Moen Kopje Formation. Many of the red beds of the Moen Kopje Formation were clearly deposited as tidal flat deposits. So that takes us through the rock record. We'll end here in the western Grand Canyon, looking at Toroweap Point, and at the bottom of the slide, the Cambrian rocks all the way up through the Permian rocks with the Kaibab Formation at the very top on the distant point. So there we've seen the history of the Paleozoic rocks of the Grand Canyon, and they're there to be seen, beautiful rocks exposed in this part of the world. Thank you for your attention.
Great. Well, thank you very much, Dr. Blakey, for taking us through all those different layers of rock. I love visualizing the different environments that may have, did exist, at various times when those layers are being deposited, and actually trying to visualize the geography of North America, like you have with your maps, just makes it even more, I think, powerful and more fascinating to imagine what Earth might have been like when these different layers were being laid down. So thank you for that.
You're welcome.
I really appreciated your discussion there towards the beginning about the Grand Staircase. It's something I like to talk about here, because a lot of folks visiting Grand Canyon, a lot of them are coming from Utah, or they're about to go up to Utah. They either came down the staircase or they're about to go up it. So when you tell them that, for example, like the Kaibab here at the top of the canyon is the lowest layer that you can see exposed up at Zion, and then the top layer at Zion is then the lowest layer exposed up at Bryce Canyon. It really helps them visualize what exactly they're seeing as they drive up into Utah, or down to here to the canyon from Utah. So yeah, and the tilt, the fact that they're tilted like that, is also something I like to talk about here at Grand Canyon, because to explain, of course, why the North Rim is over 1,000 feet higher than the South Rim is, and that shows you, I think, really how how much of an effect just a very slight dip in layers of rock can have. It's only like a 1 to 2 degree dip here across Grand Canyon, but that translates over 10 miles to about 1,000 feet of elevation change. So, yeah. All right. Let me see. And and one other thing I really like that you mentioned is the idea of accommodation space, of accumulation of sediment that has to have a place to accumulate in. And a very, very common question here at Grand Canyon is they look out at this vast hole in the ground, and you tell them that it's formed by erosion, and they ask, well, where did it all go? Where's all the rock that used to be here? If it was formed by, river erosion and other erosional processes, where did it all go? And I'm like, well, it's in the ocean. It's out in the ocean. It's in the Gulf of California. They're growing crops in it in the Imperial Valley.
Yeah.
And then
And oftentimes I'll like to mention that, in the Gulf of Mexico, there's like 50 to 60,000 feet worth of accumulated sediment. There's like 12 miles on, thick of sediment in the Gulf of Mexico. And that this was when these rocks were deposited, it was a kind of a similar environment. It was a passive environment off of a coastline where just erosion is just carrying material down into the ocean and or along the shoreline and piling it up. So, yeah. So yeah, thanks for covering all of those ideas, because I think it'll help folks understand maybe where all these how all these rocks got here. So.
Well, that's about it for today's first full day of talks here for GeoFest 2020. Of course, today we were talking about Grand Canyon's 3 sets of rocks. And I hope you enjoyed all of those talks. I hope you learned a lot. I know I did. And I also hope you enjoyed me taking you down the South Kaibab Trail to have a look at all of those rocks. Well, almost all. Not the Chuar group, unfortunately. We're actually looking down on the South Kaibab Trail right now. The sun's getting ready to set off there to the west, and it's been a long day, but hopefully a productive one for you all out there. I think hopefully we've set the stage for the rest of the talks here this week with these talks about all the different rocks that are found out there in Grand Canyon. Over the course of the week, we're going to be delving into all of the amazing stories that all those different rocks out there in the canyon tell us about the history of our planet, even about the history of life on Earth. So I hope you'll continue to join us each day for the rest of the week. We have a lot of really, really amazing talks lined up on a lot of different subjects. Tomorrow, we're going to be focusing on unconformities, missing time, gaps in the geologic record. And oddly enough, gaps in the record, missing time, even that actually tells us a lot of different things. We're going to be talking all about that tomorrow. So I hope you'll join us, and thanks for being here with us today. Have a good night.